Welcome to the deep dive. Today, we're tackling something pretty fascinating in the world of large language models, LLMs, specifically how they handle really, really long inputs, think whole books, massive code bases.
Right, these huge sequences.
Exactly. And this is a real challenge. The standard approach, often using transformer models, they're powerful, no doubt, but they get incredibly computationally expensive as the input gets longer.
That quadratic complexity issue, it just balloons.
It really does.
And, well, that expense is exactly why we've seen this exciting development of recurrent LLMs. They're built differently, aiming for more efficiency with these long contexts.
More efficient how, exactly?
Well, they have what's called subquadratic prefill complexity. That's the initial processing, and then, crucially, constant decoding time when they generate text. So much better scale.
Okay, so you'd think problem solve for long context, right? Recurrent models are the answer.
That's what you'd expect, yeah. But it turns out maybe not quite so simple. Our deep dives today is looking into a newly identified limitation, even in these advanced recurrent models, when they face really long inputs. They're calling it memory overflow.
Memory overflow sounds problematic.
It's a really interesting, almost paradoxical situation. I mean, these models are designed for long contexts, trained on them sometimes.
Right.
But the research we're looking at suggests there's a kind of fundamental limit. Their recurrent memory has a fixed size, basically. And if you push too much information in, it just gets overwhelmed.
Overwhelmed and then performance drops.
Exactly. You see a noticeable dip in how well they perform the task.
Okay, let's really unpack this. We've got the research paper itself, a study guide, some background notes. Looks like a good set of sources. The core idea is this memory overflow. How do the researchers actually investigate this? How do you test for memory overflow in an LLM?
Yeah, they used a pretty clever method called the associative recall task, or AR task.
Associative recall. Can you maybe give us a simpler way to think about that? An analogy, perhaps?
Sure. Imagine you're shown a bunch of flashcards, each with a name on one side and a face on the other. You study them. Then someone shows you just a face and asks for the name.
Okay, simple memory test.
Pretty much. For the LLM, the flashcards are key value pairs fed into its context. Think of them as little facts, like Paris, France, apple fruit. Then the model gets a query, just the key, like Paris, and it has to output the associated value, France.
So it's testing if it can hold on to and retrieve specific little facts embedded within a potentially long stream of information.
Exactly. It's a direct probe of its memory and retrieval ability within that context window.
Makes sense. So what did they find when they ran these AR tests?
Well, the findings were quite stark, actually. They used a pretty capable model, Falcon Mamba in 7B, a 7 billion parameter recurrent model.
Okay.
And even this model showed a significant drop in accuracy, remembering the right value as they increased the number of facts, the key value pairs, in the context.
And this was only for super long contexts.
That's the surprising part. No, this overflow-like behavior, as they call it, started happening even with relatively short contexts. We're talking around ND 1200 tokens.
1,200 tokens. That feels really quite short for a modern LLM designed for length.
It does, doesn't it? It suggests that even before you get to, processing huge documents, these models might be hitting some kind of internal memory limit.
So they dug deeper into this.
They did. They ran more controlled experiments using simpler models, just two-layer Mamba models. This is shown in Figure 2 in the paper. And those tests really confirmed this overflow idea.
Okay.
They even tried increasing the hidden state size of the model. You'd think bigger memory, less overflow, right?
Seems logical, yeah.
It helped a bit, but it didn't prevent the overflow. It still happened, just maybe slightly later, which really points towards maybe an inherent architectural limitation, that these standard recurrent models with their fixed memory might fundamentally struggle to scale to arbitrarily long or information-dense inputs.
Wow, okay, that's a pretty significant academic point then. The architecture itself has this bottleneck. So problem identified, memory overflow. What about the solution? The researchers proposed something, right?
Yes, they did. And it's quite innovative, especially because it's a training-free method. It's called OPRM, Overflow Prevention for Recurrent Models.
OPRM, training free sounds good, means you don't have to retrain existing models.
Exactly. It's an inference time strategy. And the core idea is actually quite intuitive. Manage the context processing before the model gets overwhelmed.
How does it manage it?
Basically by chunking. It uses a kind of divide and conquer approach instead of feeding the whole massive input context to the model at once.
You break it down.
Precisely. You break it down into smaller, manageable segments or chunks. The key is that each chunk is sized so it doesn't exceed the model's memory capacity. It's like instead of trying to read and memorize an entire encyclopedia in one go, you read it chapter by chapter.
Okay, that makes a lot of sense intuitively. So what are the actual steps in OPRM? How does it work mechanically?
There are essentially two main stages. First is speculative prefill.
Speculative prefill?
Right. Here, the long input context is split into these chunks, usually of a fixed length. Let's call it L. Now, each chunk is processed independently by the recurrent model.
Independently.
Yes. And importantly, each chunk isn't processed in isolation. They prepend the original prefix of the whole input and append the suffix, which usually contains the actual question or query you want answered.
Ah, so each chunk still has the beginning and the end context, including the question.
Exactly. And because they're processed independently, you can do this in parallel, which is great for efficiency, potentially faster.
Okay, so you process all these chunks in parallel, each with the prefix and suffix. What happens next?
That brings us to stage 2, selective decoding. After processing all the chunks, you have multiple potential states or memories from the model, one for each chunk. OPRM then needs to figure out which one of these states is the most promising for generating the answer.
So it doesn't try to combine them all.
No, and that's a key part of the innovation here. It selects one chunk state and performs the standard autoregressive decoding, generating the answer token by token using only that state.
Interesting, just picks the best one. How does it decide which chunk is best? It can't just be random, right?
No, definitely not random, although they did test random selection later, interestingly. They proposed two main criteria for selecting the best chunk. One is based on entropy.
Entropy, like uncertainty.
Exactly, information theory stuff. The entropy-based man selects the chunk where the model is most confident about the very first token it predicts for the answer. High confidence means low entropy in the probability distribution for that first token.
Okay, so the model's essentially signaling, based on this chunk, I have a really strong feeling about what the answer starts with.
That's a good way to put it. The thinking is, if the MADI is very sure about the start of the answer after processing a chunk, that chunk probably contained the relevant information.
Clever. What was the other method?
The other one was probability-based. This one tries to pick the chunk that maximizes the probability assigned to the query tokens themselves, which are in the suffix.
So if processing a chunk makes the question itself seem more likely or relevant according to the model, pick that chunk.
That's the idea, but the paper mentions this one was empirically a bit unstable. Apparently, the probability values often ended up being tiny, effectively zero, making it hard to reliably compare chunks.
Ah, okay. Vanishing probabilities, perhaps. So the entropy method seems like the go-to?
It seems to be the more robust and effective one in their experiments, yeah.
Got it. Now, there was also something called an IDK filter. I don't know.
Right, the IDK filter. This is an extra refinement, particularly useful for things like document question answering. The idea is you first instruct the model that if it thinks the answer isn't in the provided text, it should output a special error or IDK token.
Okay.
Then, during the OPRM process, after the speculative prefill, you look at the first token prediction for each chunk. If a chunk predicts this error token, you just discard it.
Because the model thinks the answer isn't in that piece of text.
Exactly. If by some chance all chunks predict error, they just keep the first one as a fallback. But usually this filters out irrelevant chunks. Then you apply your main selection criterion, like minimum entropy, to the remaining potentially relevant chunks.
So it's a way to stop the model from just guessing an answer based on an irrelevant chunk when the real answer isn't actually there.
Precisely. Improves reliability, makes the model more likely to say, I don't know, when it genuinely doesn't.
That sounds really useful. Okay, so we have the problem memory overflow and the solution OPRM with its charking, selection criteria, and IDK filter. Let's talk impact. Did it actually work? How well?
Oh yeah, the results they present are quite impressive. They tested it on LongBench, which is a standard benchmark for long context LLM performance.
Right.
And OPRM provided significant boost across the board for various recurrent models, Falcon Mamba, recurrent Jenna, RWKV models. We're talking improvements up to, I think, over 50% in some task categories.
Wow, 50%? That's huge.
It really is. And crucially, the benefits were more pronounced for longer context lengths, like 8K tokens and beyond, which directly supports the idea that it's fixing that overflow problem, which gets worse with more length.
So with OPRM, these recurrent models are suddenly much more competitive in the long context game.
Very much so. And academically, this is where it gets really interesting. They tested on the harder LongBench V2 benchmark as well.
Mm-hmm.
And recurrent models using OPRM actually achieve state-of-the-art results among models in the roughly 7 billion parameter class. They even beat similarly sized transformer models in some cases.
Whoa, hang on. Recurrent models beating transformers on long context tasks, that kind of goes against the conventional wisdom, doesn't it?
It really does. It challenges that established view that transformers just inherently own the long context space.
So what happens at truly extreme lengths, like way beyond 8K?
That's another fascinating finding. The paper suggests that as you push context lengths out further, think 32K, 64K, even 128K tokens and more, these recurrent models with OPRM actually start to gain an advantage over transformers.
Even if the transformers are using their own tricks for handling long context.
Yeah, even when compared to transformers using context extension methods, it suggests OPRM isn't just letting the model see more context, it's helping it process that massive amount of information more effectively by avoiding the memory bottleneck. It's tackling a more fundamental issue.
So it's about effective processing, not just raw input length capacity.
Exactly. And they tested this idea directly too, looking at context extension performance, how well models trained on, say, 4K tokens generalized to 32K tokens.
Right.
They found OPRM outperformed other methods specifically designed for context extension, like Decimaba or Longmamba. The paper argues those other methods might stretch the context window, but they don't solve the underlying overflow problem within that window. OPRM's chunking does.
That makes sense. Did they do ablation studies, like taking OPRM apart to see which bits were most important?
They did, yeah. Those studies gave some really cool insights. As we discussed, the minimum entropy criterion consistently came out on top for chunk selection, especially for longer stuff.
Okay.
But here's a kicker. They found that even just randomly selecting a chunk sometimes performed better than the baseline model trying to process the whole long sequence without OPRM.
Random selection was better.
Sometimes, yeah, which just highlights how badly the memory overflow must be hurting the baseline performance. It's better to focus on a random part than to get overwhelmed by the whole thing.
That's incredible. Really drives home the point about the overflow problem. What else did the ablations show?
They confirm the IDK filter helps, particularly for document QA tasks, boosting accuracy for most models. They also looked at the chunk size, LA.
Right. How big should the chunks be?
Seems like it's fairly robust. Within a reasonable range, the performance didn't change dramatically, which is good news for practical implementation. You don't need to fine-tune it perfectly.
Okay. But you mentioned something earlier about the academic significance of the single chunk decoding strategy being successful.
Yes, that's maybe one of the most thought-provoking aspects from a research standpoint.
Why is that?
Well, think about it. Recurrent models are supposed to be good at handling long-range dependencies, integrating information across the entire input sequence. But OPRM achieves great results by focusing decoding on just one chunk.
Right.
The fact that this works so well raises a really fundamental question. Are current recurrent LLMs actually effectively using information from very distant parts of the input? Or are they maybe relying more on relatively local context, even with their recurrent architecture?
So the success of focusing on one chunk suggests maybe they aren't truly integrating across the whole long context as well as we thought?
It strongly suggests that yes, or at least that the way they currently do it might not be optimal, and that focusing attention via chunking can be more effective in practice. It really opens the door for future research into how these models actually process long-range information and how we can improve that.
Fascinating. So OPRM seems like a big win, but are there downsides? Limitations?
Yeah, the researchers are upfront about those. Firstly, because it's training free, its ultimate performance ceiling is set by the quality of the base recurrent model you apply it to. Garbage in, garbage out, essentially.
Fair enough.
Also, the current version focuses decoding on a single chunk. It doesn't try to explicitly combine information across different chunks. Maybe there are cases where the answer requires synthesizing info from multiple separate parts of the document. OPRM wouldn't handle that directly right now.
So potential for future weak there, maybe some kind of cross-chunk mechanism.
Exactly. They suggest that as a future direction. And as mentioned, things like the IDK filter might work slightly differently depending on the specific base model.
Okay. What about speed and memory? Does all this chunking add a lot of overhead?
Interestingly, maybe not as much as you'd think. Their analysis suggests that for very long contexts, OPRM can actually be faster overall than the baseline.
Faster? How?
Because of that parallel processing during the speculative prefill stage, processing many smaller chunks in parallel can be quicker than processing one massive sequence sequentially. Memory usage might go up a bit since you need to store states for multiple chunks temporarily, but it seems to remain competitive overall.
Right, because the state size itself is usually smaller than the model parameters. Okay, let's try and wrap this up. What's the main takeaway message from this deep dive into OPRM and memory overflow?
I think the core message is twofold. First, this research clearly identifies a significant, previously underappreciated problem memory overflow that limits even sophisticated recurrent LLMs on long contexts.
Okay, problem identified.
Second, and more importantly, it offers a really elegant and effective solution. OPRM is this simple, training-free inference technique that provides substantial performance gains. It lets recurrent models punch way above their weight, making them truly competitive, sometimes even superior to transformers in the long context arena.
And beyond just benchmark scores, this has wider implications for AI research.
Definitely, academically, it forces us to reconsider how recurrent models handle long sequences and maybe question some assumptions. It opens up new research questions about long-range dependency processing. And practically, the success of an inference time fix like OPRM is exciting. It suggests we can get more out of existing models without costly retraining.
So, for anyone listening who works with LLMs, especially on tasks involving lots of text, this is pretty important stuff to know about. It highlights the strengths and, critically, the fixable weaknesses of recurrent models.
Absolutely. It shows the field is constantly evolving, and clever techniques can really shift the balance between different architectures for specific challenges.
Which brings us perfectly to our final thought for you, the listener. Given how well this relatively simple chunking strategy works to overcome memory limits, it really makes you wonder, how could we design future LLM architectures from the ground up to inherently handle and integrate information across vast contexts more effectively without falling prey to these overflow issues? What might that next generation of truly long context models look like? Definitely something to ponder. Thanks for joining us for this deep dive.